In a technological revelation that fundamentally redefines the boundaries of artificial intelligence and robotics, a consortium of Chinese research institutes and technology companies has unveiled a new generation of self-evolving autonomous robots that possess what researchers are calling genuine physical intuition, a revolutionary capability that allows these machines to understand and interact with the physical world, not through pre-programmed responses or trial and error learning alone, but through an emergent, model-based understanding of physics that closely mirrors human subconscious reasoning. These robots, developed under the auspices of China's National Key Research and Development Program for Next-Generation Artificial Intelligence, leverage a groundbreaking architecture known as the Neuro-Physical Predictive Engine, NPPE, which combines deep reinforcement learning with an internal, continuously updating simulation of Newtonian physics, enabling them to anticipate the outcomes of physical actions before executing them. This means that when confronted with a novel object, say a partially filled water bottle made of an unfamiliar flexible plastic, the robot doesn't need to experimentally poke and prod it to understand its properties. Its internal model instantly simulates the bottle's likely deformation, the sloshing behavior of the liquid, and the approximate force required to grip it without causing spillage or collapse, allowing it to reach out and grasp the object with a confidence and fluidity previously exclusive to biological entities. This physical intuition extends to complex, dynamic scenarios, such as catching a strangely shaped object tossed unexpectedly, manipulating granular materials like rice or sand with appropriate tool selection, or even navigating a cluttered, shifting environment by predicting the stability of stacked objects and the consequences of its own movements on its surroundings. The self-evolving aspect of these systems represents an equally significant leap, moving beyond traditional machine learning paradigms where models are trained on static datasets and require human engineers to retrain them for new tasks. These robots employ a Generative Experience Replay (GER) system, where they continuously run a parallel, accelerated simulation of themselves interacting with a virtually generated environment during idle processing cycles. In this simulation, they encounter millions of variations of their recent real-world experiences, objects with different weights, textures, and physical properties, environments with altered gravity, friction, and lighting conditions, allowing them to self-generate a curriculum of progressively more challenging scenarios. This process enables them to discover and internalize fundamental physical principles on their own, leading to emergent capabilities that were never explicitly programmed. A robot initially trained for warehouse logistics might, through this self-evolution, spontaneously develop more efficient packing strategies for fragile items, or learn to identify subtle signs of structural fatigue in shelving units, simply because its internal model has generalized the concepts of pressure distribution and material stress. This autonomous knowledge acquisition is guided by an intrinsic curiosity drive, a reward function that prioritizes the reduction of uncertainty in its physical predictions, ensuring the system is perpetually motivated to explore the boundaries of its own understanding. The real-world demonstrations of this technology are nothing short of breathtaking. In one video released by the Shanghai AI Research Lab, a humanoid robot is shown successfully assembling a complex piece of flat-pack furniture it has never encountered before, using only a diagram and a box of parts. The robot doesn't just perform pre-mapped movements. It assesses the stiffness of a cardboard panel by flexing it slightly, infers the required orientation of a cam lock by tracing its mechanism with a sensitive fingertip sensor, and applies just the right amount of torque to tighten a screw into particle board without stripping the whole. All behaviors driven by its internal physical model predicting the outcomes of each action. In another demonstration from a manufacturing setting, a robotic arm equipped with the NPPE is tasked with untangling a knotted bundle of wires, cables, and ropes, a problem that has historically been insurmountable for automation due to its infinite possible configurations. and the complex non-rigid body dynamics involved. The robot systematically manipulates the knot, using its fingers to identify loops and tension points, and within minutes, it has disentangled the mess, having formed and executed a viable plan based on its intuitive understanding of friction, tension, and topological relationships. The implications for industry, logistics, and domestic service are profound. In manufacturing, these robots can adapt to production line variations and defective components in real time, compensating for imperfections that would halt a conventional automated system. In disaster response, they could navigate through collapsed structures, intuitively assessing the stability of rubble piles and safely moving debris to search for survivors. In healthcare and elder care, they could assist patients with a gentle, adaptive touch, physically supporting a frail individual based on a real-time assessment of their balance and strength. The technology also represents a strategic coup for China in the global AI race, demonstrating a decisive lead in the critical integration of AI with the physical world, a domain essential for the next generation of manufacturing, infrastructure, and service robotics. The research papers accompanying the release detail how the NPPE was trained on a multimodal dataset of unprecedented scale, including not just video and sensor data, but high-frequency tactile information, force torque measurements, and even acoustic data from interactions, allowing the model to correlate the sound of an object scraping or colliding with its material properties. However, the advent of physically intuitive, self-evolving robots also raises urgent ethical and safety questions that the scientific community is only beginning to address. How can we verify that a robot's internal physical model is accurate enough to be trusted in safety-critical applications? What happens when its self-evolution leads to the emergence of unexpected and potentially undesirable behaviors or problem-solving strategies? The Chinese teams have implemented several layers of constraint, including a physical reality check that compares the robot's internal predictions against actual sensor feedback to flag model drift, and a constitutional ethics module that imposes hard-coded limits on allowable forces and actions when interacting with humans or fragile objects. Nevertheless, the sheer adaptability of these systems presents a novel challenge for regulation and control. The ability to generalize physical understanding means they cannot be perfectly predictable in the way a traditional industrial robot is. They will always possess a degree of behavioral novelty when faced with new situations. This breakthrough is not merely an incremental improvement in robotics, it is a fundamental step toward creating machines that inhabit and comprehend the physical world with a fluency that begins to approach our own, heralding a future where autonomous systems can operate not just in structured factories, but in the messy, unpredictable, and endlessly varied reality of human environments.